Hi, this is Boyan from UC Santa Barbara. Today we are going to talk about EGEMM-TC, accelerating scientific computing on tensor cores with extended precision. So first we will talk about motivation. Why do we care about emulation on tensor cores? Nowadays, generally only low precision matrix computation are supported on many specialized cores. For example, there is half precision computation on NVIDIA Tensor cores. However, high precision matrix computation are generally required by scientific computing applications, such as k-means, k-radix sort, and stream compaction. So if we want to support these scientific computing applications on tensor cores, then we need the emulation. Previously, there is one method called Decker's method. It is developed for CPUs. Actually, it utilizes 16 half-precision instructions for emulating the computation with 21 metadata base. However, naively borrowing Decker's method to the tensor cores does not work, since it has at least 16 times overhead. Remember that on tensor cores, the half precision computation is only 8 times faster than the single precision computation on CUDA cores. This 16 times overhead can easily make it quite slow to run the code on the tensor cores. Recently, there is a MACDIS method. It is developed for GPUs. It's utilized for half-precision instructions for 20 metadata base. However, this approach has low performance since it does not have system-level optimizations. It also has one less bit than the Decker's method. In this table, we summarize four different data types: the half precision, single precision, MACDIS precision, and extended precision. The main difference is on the metadata bit. Note that the single precision has 23 metadata bit and half precision has 10 metadata bit. In this work, we achieve the extended precision with 21 metadata bits. There are several challenges in emulation on tensor cores. First, we need some emulation algorithm design. We need to achieve extended precision with a small number of instructions. Once we have this emulation algorithm design, we also need the system-level optimizations to efficiently mapping the workload to tensor cores. Actually, we need to explore the new computing primitives and memory hierarchies from tensor cores. The third thing is the design space exploration. Actually, there is a large hyperparameter design space. We want to reduce manual efforts and avoid trial and error strategy. We summarize our contribution in this figure. Given the scientific computing applications and the data such as matrices, we first designed the emulation algorithm such that we can run the emulation on tensor cores with low theoretical overhead. Then we have some tensor core kernel optimizations that efficiently maps our workload to tensor cores. It includes the tensor core centric tensorization to split the large matrix into much smaller matrix and map it to the tensor core. It also includes sublevel optimization to further improve the performance. The third part is the hardware-aware analytic model, which can automatically explore the design space. Finally, all of these three parts lead to efficient execution of the emulation and the scientific computing applications on tensor cores. Now we will first talk about the emulation algorithm design. We have designed a generalized emulation design workflow. Our key insight is that we can explore the high precision intermediate results to help our emulation. First, we have a precision profiling process. We use the high precision random number generator to generate some randomized data input, feed it into the specialized core compute primitive, and get the specialized core results. Meanwhile, we have several probing compute primitives on the different possible precision of the intermediate result. We run this probing compute primitive on CPUs, and it takes the same set of randomized data input and gets the results. We compare these CPU results bitwisely with the specialized core results. If two results are the same, then we can know the precision of the intermediate result. Once we have this precision profiling, we have the emulation design. Given some extended precision input, we do the data split into several low precision input. Then we feed each low precision input into the specialized core compute primitives and get the intermediate result. Generally, this in our workloads and on Tensor cores, this intermediate result has a higher precision than the low precision input. Finally, we combine all these intermediate results into the extended precision output as a final result. Okay, so now we will talk about our emulation algorithm design in detail. We first do the precision profiling on Tensor cores. This is a code snippet for our profiling. We first randomly generate some half precision data, like this A1, A2, B1, B2. We use it to initialize the fragment A and B for Tensor cores. And then we use this MMAsync API to do the computation on Tensor cores and get the final result in fragment D. Meanwhile, we have two probing compute primitives on CPUs. One is a half precision addition and multiplication. Another one is a single precision addition and multiplication. We would like to use this one as a baseline and compare it bitwisely with the result from Tensor cores. In this way, we can know the precision of the intermediate result on Tensor cores. Our observation is that the Tensor core produce extended precision intermediate results with 21 metadata. Once we have this precision profiling, we can talk about our emulation design. In this algorithm, we show our lightweight stream emulation design. So when we design this algorithm, we keep in mind that we need an algorithm with low overhead. We only want to use a small number of instructions, so the overhead is small and the performance is good. Actually, we take three matrix inputs, A, B, C. All of them are single precision input. We do the data split. We split matrix A into A low, A high. Also, we split matrix B into B low, B high. After that, we call the tensor core for 4 times for combination of A low, B low, A low, B high, and so on. And the final result is stored in the matrix D. Here, note that the matrix C and D are both single precision data, which are supported natively on the tensor cores as the accumulator. In this algorithm, the theoretical overhead is 4 times computation overhead, since we call the tensor core for 4 times. Also, there is a 2 times memory overhead if we do some data reuse. For example, we reuse a load for 2 instructions instead of loading them independently. We also have some data split algorithm design. Here we want to emulate. Here we want to emulate the computation of single precision, which has 23 metadata bits. In the truncated split, we can use use 2 half precision data to represent 1 single precision data. Actually, in each half precision data, we have 10 metadata bits. So in total, we have 20 metadata bits here. A better design is the round split. We additionally have 1 extra bit. So in total, we have 21 metadata bits in total. Actually, this 1 extra bit comes from the sum bit of 1 of the half precision data. So now we have 10 metadata bits from each of the half precision data. We also have an additional 1 sum bit from 1 of the half precision data. So in total, we have 21 metadata bits. In this data split algorithm, we need to do the data split for each element once. So there is a n square overhead. Note that this overhead is negligible compared with the EGEMM operation, which requires n cubic overhead. So now we have our emulation algorithm design. If we want to run the workload efficiently on tensor cores, we still need some system-level optimization. Actually, we need the tensor core centric tensorization to efficiently map this workload to tensor cores. There are several challenges. First, we need to map these large matrices to tensor cores. Generally, our workload may have 100 by 100 matrix cells, or even 8,000 by 8,000 matrix cells. However, the tensor core usually only support 16 by 16 or 8 by 16, this small matrix tile. Also, we want to explore the collaboration across VAPs and within VAPs. We also want to explore the new memory hierarchy architecture called fragment from tensor cores. So first, we have the tensorization and VAP collaboration. Our key observation is that there is abundant data reuse opportunities in our workload. So we split the EGEMM workload into 2 phases. The first is the data loading phase. The second is the computation phase. In the data loading phase, all the VAP collaboratively load data from global memory to the shared memory. Then in the computation phase, each VAP will individually load data from shared memory to fragment. In this way, we can reduce the memory access from the global memory and achieve speed up. The second optimization is the intra-VAP fragment caching. We want to cache matrix tiles in fragment. So in this way, we can reduce the global memory access. In this table, we summarize the memory access on each GPU VAP with and without fragment caching. Generally, we can save the memory access by several times. So we also have some instruction level optimizations. First, we have the register enhanced instruction scheduling for latency hiding. We illustrated it in this figure. Actually, we split our workload into several iterations. At each iteration, we load data from shared memory and use this data in the fragment for the computation with HMMA instruction. Meanwhile, we also had latency by loading the data from global memory to the shared memory. This data is loaded for the next iteration. So In summary, we simultaneously have two parts of latent hiding. One is between the loading data from shared memory and HMME computation. Another one is loading data from global memory for the next iteration. Also, we have the register allocation design to avoid register spelling. Actually, we found that our workload can be split into several stages, and there are part of the registers that are used only in a single stage, so we can reuse registers across stages. Note that this register allocation is very important for the performance. Actually, if we do not have this register allocation, we may have some register spelling and face some slowdown. Okay, so the third part of our work is a hardware-aware analytic model. We want some automated hyperparameter selection. Actually, there are 6 parameters in total in our workload. The first set is the BM, BN, BK. They are the block tiling sets. Also, we have the WM, WN, and WP for the warp level tiling sets. All these parameters are very important for the number of memory access and the latent hiding. So the first thing is memory access. We want to select the block size to improve the ratio between computation and the global memory access. A higher ratio usually indicates a better performance. After some computation, we can use this formula to summarize this ratio. For the detailed the computation procedure, please refer to our paper. The general pattern here is a larger block size usually leads to a higher ratio, which means a better performance. Actually, this ratio has very significant impact on the performance. It may lead to 2 times or even more difference in the performance. Also, our key observation here is that this ratio is independent of the BK. So our strategy is to select smaller BK and leave space for larger BM and BN. This is important, especially when there is a constraint on the shared memory side. The second part is latency hiding. Our goal is to make sure that the computation time is larger than the memory access time on each warp, so we can completely hide the memory access latency. Our key observation here is that a larger warp size usually leads to a lower memory access time on each warp. So we want to select larger warp size and get a better performance. Okay, so now let's talk about the final result. On the emulation precision, we compare with 2 baselines. One is the mark-disk method that we have mentioned earlier. Another one is the Kublas kernel on Tensor cores with half precision. We see that from small matrix of around 100 to large matrix of around 8,000, we can significantly reduce the emulation error. On the performance part, we compare with both the vendor kernels and the open source kernels. First, on the vendor kernels, we compare with the Kublas kernel on CUDA cores with single precision result. Also, we use the Kublas kernel on Tensor cores with half precision to implement our emulation algorithm. Here we see that our EGEMM-TC can outperform both baseline kernels by a large margin. We also compare with the open source kernels. Actually, we compare with the CUDA SDK kernel that runs on CUDA cores with single precision. We also compare with the mark-disk method. We say that we can achieve more than 12 times speed up compared with the CUDA SDK code. Also, we achieve around 3 times speed up compared with the market method. Finally, we show our results for scientific computing applications. On k-means, we can achieve around 1.8 times speed up. For k-n, we can achieve more than 2.2 times speed up. Okay, so that's all for my presentation. Thanks for attention.